to the April 2014 edition of the Pohle Colloquium. Brief announcements. Next month, the 7th of May, Nicholas Scoville from Ursinus College, and he'll be talking actually about some of the early history of point set topology. And we know that Bill Dunham will be speaking at some point in the fall. We're not sure when in the fall, but he will be coming. And we're starting to put together the schedule for 14-15, so if you have any suggestions or any of you would like to volunteer, please let me know. And I guess that's all of the announcements. So without further ado, I want to introduce someone who probably needs no introduction to most of you guys. Lee Stemkoski has been at Adelphi since a little before the Euler tercentenary.
That's true.
He came here in 2006. His PhD is from Dartmouth University. His undergraduate degree from Boston University. It's fitting that we should have a talk about Euler this month because Euler's birthday was April 15th, long before there was such a thing as income tax. So we're coming up on Euler's 307th birthday. And possibly in part through recognition of that, Lee will be talking to us today about the work of Leonhard Euler in number theory and the Commentationes Arithmeticae. Lee.
Thanks, Rob. All right, well, I come to this from kind of 2 or 3 different perspectives. I love number theory. My PhD was in analytic number theory, but I also love the history of mathematics because it's so interesting. But I'm also kind of a technological guy, and I like data analysis. I like to collect data and organize it, and I created this website called the Euler Archive with Dominic Levy and Eric Tao and a whole group of people, and every once in a while we try to update it and improve the quality of the records. And so I've been looking at the number theory records, trying to get kind of a feeling for everything Euler did in number theory and trying to come up with a better way to categorize it. Because right now, you click on number theory and you just get a list of all of Euler's number theory, just based on the date he presented it. You know, there's no kind of pedagogical ordering to this, just kind of a list. So I wanted to get a handle on what he did in number theory so I could better organize it and disseminate it. So in this talk, I'm going to talk about a couple of things. Before we talk about what Euler did in number theory, I'd like to give a little bit of prehistory, the origins of number theory. There's kind of a very strong thread here from Euclid to Diophantus to Fermat to Euler. They all kind of worked on the same problems. They just kind of made them more sophisticated along the way. And I'm going to talk about what Euler did in number theory, and in particular, I'm very interested in these 2 later works. They're actually both published posthumously. One of them, actually I'm going to talk about E791 first, that's 791 in the Enstrom Index. It was actually published in 1849. It's kind of a collection of all of Euler's number theory, which is the kind of stuff I'm interested in. You know, what did Euler do in number theory? But then if you want to organize it in a way that makes sense, there's a way to do that from E791, and there's also a manuscript of a number theory textbook Euler started to write, E792. I'm going to talk about kind of how these 2 are related and what I'm going to do with this information in the future. And then kind of what did Euler leave unfinished and how we could proceed from there. But first, I'd like to start with, well, just a picture. When I think of the beginnings of number theory, when my students ask me, oh, Professor Stemkoski, you're teaching number theory next year. What's number theory? So I inevitably tell them, well, Pythagorean triples, we study those a lot. 3 squared plus 4 squared is 5 squared. What other whole number solutions are there? So here we've got the Plimpton tablet, which in cuneiform lists all sorts of integer solutions, just seemingly for the fun of it. We had a method to list solutions, so list them we shall. And then, well, the first main player is really Euclid. We often think of Euclid in terms of geometry, but he was a number theorist as well. And in particular, books 7 through 9 of the Elements talked a lot about number theory, a lot of things which now carry Euclid's name. He introduced the idea of divisibility and primes. Granted, he did all this in terms of lengths of line segments, because arithmetic was very geometric to the Greeks, as most things were. Euclid introduced an algorithm, which we now call the Euclidean algorithm, for calculating the greatest common divisor of 2 numbers. Euclid created a lemma, which we now call Euclid's lemma. It says if a prime divides a product of 2 numbers and the prime divides one of the 2. And then he did a couple of interesting things which are forerunners to major results in mathematics. One of them, the fundamental theorem of arithmetic, says that every number has a unique prime factorization. And he kind of gave us an idea of how to get started. And every number is either itself prime or measured by some prime. Measured would really translate into divisible nowadays. If you're measured by a number, that means you can be split up into units of that measurement with none left over. Euclid also famously gave the first proof of the infinitude of primes, and he introduced what I'm going to kind of call forms. The idea is, if you have two odd numbers and you multiply them, you get another odd number. If you have two odd numbers and you add them, you get an even number. Euclid looked at some questions like that, but also some slightly more complicated questions, which, he didn't use the algebraic notation, but algebraically he would answer questions like, if you have a cube times a number that yields a cube, well, that number you multiplied, it must also itself be a cube. So we looked at some questions which involve the forms of numbers, and he looked at sums of geometric progressions, and all of this was kind of leading up to this result, kind of the last number theory result in one of the last number theory books about perfect numbers. A perfect number, the sum of its proper divisors is equal to itself. So for instance, 6 is a perfect number. The divisors of 6, the proper divisors, are 1, 2, and 3. 1 plus 2 plus 3, that equals 6. So 6 is a perfect number, as is 28, and there's a couple more. And Euclid actually gave a criterion to look for that. I kind of think of this particular theorem in the 9th book of Euclid. It kind of has the same feeling as the Pythagorean theorem in Euclid's early works. If you look through Euclid's first book, it seems like the results just lead you to the Pythagorean theorem. It occupies a special place. Perfect numbers similarly occupied a special place in Euclid's number theory books. And then from Euclid, about 500 years later, here's kind of the next, in my opinion, major contribution to number theory. Diophantus, Greek mathematician, wrote a collection of 13 books, but only 6 of which survived. And they're basically collections of problems which are asking us to find integer solutions to equations, to particular equations. And so just for an example, here's one of the problems from the books. I think there are about like 130 of these problems around there. And again, the Greeks didn't have this algebraic symbolism, so imagine this being much more wordy. Given a square number 16, let's say you want to divide that number into 2 squares. So find 2 squares whose sum is 16. X squared is one of the required squares, and he gives this kind of algorithm. If this is one of the squares, then we do some subtraction. This must be a square. And then he uses this very magical method, which happens to give us a correct answer in terms of fractions. Not a very generalizable method, not something which is explained. You can't really learn from this. So I'm not sure why he wrote this series of books. But it exists, and this set of problems, or this type of problems, are still called Diophantine equations after Diophantus. If you have some kind of an algebraic equation and you're looking for integer solutions or rational solutions. This is another topic that is going to come back to appear in Euler's work a lot later on. And again, these are just kind of some of the problems, again, written in algebraic notation, the kinds of things that Diophantus would work on. So when the sum of 2 squares is a square, the sum of 2 squares is equal to the sum of 2 other squares. If you have a certain number, can you write that as the difference of 2 squares? Like a lot of variations on this kind of problem. Right now, fast forward to Fermat. This is hundreds and hundreds of years later. But Diophantus was kind of the last major word in the type of problem that Fermat was interested in. So there's kind of a famous translation. Bachet translated Diophantus's Arithmetica, which we just saw on the previous slide. And Fermat's famous for having written some notations in the margins. Things like, there's that statement about the sum of 2 cubes cannot be written as a cube, but the margin is too small to contain it. That and lots of other comments which he left for future mathematicians to solve. And so we have Euler. Now Euler, you guys know who Euler is, but these are the 4 reasons I love Euler. He wrote a lot of stuff. He wrote about a wide range of things, but in a lot of those areas, his investigations were very deep, and I love his presentation style, how he goes through examples that slowly ramp up in difficulty before he tackles a general case. Now, Euler got his start in number theory through a correspondence with Christian Goldbach, about 196 letters, and almost very innocently, this is one of the first letters that Goldbach wrote to Euler, kind of as a postscript. He let Euler know about some of the interesting mathematics that Fermat was working on. So he's talking about, I don't know, Bernoulli and his theorems, and oh, by the way, Fermat observed that numbers of this form, 2 to the 2 to the x minus 1 plus 1, for certain values of x, these are going to be prime numbers, but he's not sure if there's a rigorous demonstration of this. Kind of a footnote, and the rest is history. Euler uses this as his starting point. He starts to investigate these works, and then he starts to make huge contributions in number theory. He wrote probably around 100 papers, give or take, so a major percentage of his work falls in the area of number theory. Now, how do we make sense out of all that work? So, long after Euler passed on, in the 1840s, they're putting together the Opera Postuma, and Bunyakovsky asks number theorist Chebyshev to help collect and prepare a collection of Euler's number theory works. It's a possibly massive undertaking. So I'm actually going to show you part of this. This leads to the work called the Commentationes Arithmeticae, if I'm pronouncing that correctly. It's basically a list of all the works related to number theory that Euler ever worked on. And you could take issue with this list. For instance, it includes things which are numeric that we might not think of number theory. So for instance, Euler's famous paper on the knight's torque, having a knight jump across the chessboard and hit every square exactly once. That's actually included in this collection, I guess because it's arithmetic in nature somehow. Euler's papers on Greco-Latin squares are included in this, because you could think of the entries of there as integers, I guess. Maybe discrete mathematics is kind of folded into number theory in some way. So their first job, Chebyshev's first job, was to find all the number theory publications of Euler. And so I think he's found a total of 94 that had been presented at various institutions, the St. Petersburg Academy and the Berlin Academy. And he also found, I think, 5 unpublished manuscripts, and added that to the collection. So there's about 99 altogether. But I think later on it was discovered that Johann Albrecht Euler wrote some of them, so it's not exactly 99, but it's close. But Chebyshev did a lot more than just collect his works and kind of plunk them all down. He tried to categorize them and not only group them kind of by topic area, but give you a pedagogical path through Euler's number theory. And I'm going to show you some of that in a little bit. He creates something called the systematic index. There's an index by date, but there's also an index by topic. And he even includes a brief summary of what each paper is about. That ended up being published in 1849, and right around that time too, I think Chebyshev wrote his thesis, or he wrote some major number theory, and a lot of mathematicians at the time found a lot of interesting things they started to incorporate into their own work. So a little bit of E791, short for the Commentationes Arithmeticae. This is part of the table of contents. And in the book, all the papers are actually arranged by date of publication, not date of publication, sorry, date of presentation, whenever that information was available. So this is going to kind of roughly correspond to the same ordering used by the Enneagram index. I think Enneagram used the date written to organize them. And every once in a while we don't have a presentation date associated for some of these papers. So sometimes in this column, this is the date of exhibition. There's one in 1732. There's one in 1733. The next paper, Chebyshev thinks it's between 34 and 35, then 36. And it goes on and on and on, all the way to 1782. These are all the presentation dates. And then afterwards, he includes a bunch of manuscripts, things which have not been edited or published formally. So things which were not exhibited. So for instance, this is actually E792, which I'm going to talk about in a second. The 16 books, or 16 chapters of a textbook on the doctrine of numbers, kind of what could have been one of the first number theory textbooks. And so the index we use for this book, they actually start numbering them 1, 2, 3, 4, all the way down to 90 something at the very end. Now, instead of just giving us a list and just reprinting these in order, like the Euler Archive currently has, Chebyshev went the extra mile and said, okay, I'm going to classify all of Euler's work in number theory. It's a monumental task, but he divided it into a total of 3 sections and then kind of a miscellaneous section, a melange section. So the 3 major groups, the first one was properties of divisibility of numbers. So any paper which has to do with decomposition of a number into prime factors, tables of prime numbers, Euler published some of those. He did a lot of work on sums of divisors of numbers. Amicable numbers, they also have to do with the divisors of a number. Those are all grouped in section 1, part A. And then part B, the divisibility of different formulas. You can also kind of translate this as different forms. So for instance, numbers of the form x squared plus 3y squared. Now if you have 2 factors of a number that can be written in that form, must the factors also have that same form? So answering questions about that, formulas could refer to the forms in which you could find a number, and what can you say about the factors of that? And then the theory of remainders or residues and quadratic residues. So what numbers are a perfect square modulo 5 or modulo 7? And so he's interested in answering questions like that. The second section, he starts to decompose these numbers, so something like Lagrange's 4-square theorem. In which cases can you write a number as a sum of squares? Can you write every number as a sum of triangular numbers? Can you write a number as a sum of cubes? How can you break down a number, not in terms of products, that was covered by the first section, but in terms of sums? So the first section contains decomposition into sums of powers, such as squares or triangular numbers, terms proportional to squares, which numbers can be written in the form x squared plus 3y squared, say. And then partitions of numbers kind of fall into this category as well. So for instance, if I want to take the number 5 and write it as a sum of distinct integers, I could write 5 as 1 plus 4, I could write 5 as 2 plus 3. There's 2 partitions of 5 into distinct parts. So Euler's interested in calculating things related to that as well. And that constitutes the second section of Chebyshev's organizational scheme. Now the third section is very interesting. It's like the theory of equations but applied to number theory, the types of problems that Diophantus was interested in. So we call them Diophantine analysis. And so there's kind of categories which start off with the very simple ones, and then as your exponent gets bigger, you get a later category in this list. So the determination of 2 or more indeterminates. So for instance, you might have a quadratic equation, well, almost a quadratic equation, y squared equals ax squared plus bx plus c. Can you find whole number solutions to that equation? Looks like the quadratic equation, but it's equal to y squared. Well, in order to solve that question, you need to solve a related question, Pell's equation, ax squared plus 1 equals y squared. So problems like that, where you had 2 unknowns, and you wanted to find solutions to that in either whole numbers or fractions. And some of the equations which you could not solve in this way. That's part A, and then he says, okay, after that, I'm going to say solving equations which contain. So this is just, you have 1 equation you want to solve, a system of 2 equations, that's section B, a system of 3 equations, is section C, 4 equations, section D, 5 equations, 5 or more equations is section E. And then there's this very funny last section in Diophantine analysis, which when you have a system of equations you want to solve in integers, but you have more equations than unknowns. And there's 3 papers in this section, and they all deal with grids of numbers and equations involving the rows and the columns of the grids. So things like Euler's 2 papers on magic squares are included in this group. And then there's the miscellaneous section that Chebyshev just couldn't fit other problems into one of these categories. One of them was the Knight's Tour paper. There's another really interesting paper, which is the sum of fractions where the denominators are prime, and then the sign, each term is either positive or negative depending on what the prime is equal to modulo 4. So primes of the form 4n plus 1 you add, and primes of the form 4n minus 1 you subtract. Now, can you sum that series? That somehow doesn't fit into any of these categories. It doesn't have anything to do with divisibility. You're really not decomposing a number, and you're really not solving an equation because you're given a set of numbers. So a couple of papers like that involving, primes or related things. And then, at the very end, one of the miscellaneous pieces that he found, before I talk about one of the miscellaneous pieces, this is actually part of the categorization. So if you recall when I first showed, make that large again. Back one. All right, so in the first part of the table of contents, all of the articles are arranged by date of presentation. Then Chebyshev gives us this, wrong way. Chebyshev gives us these different sections into which you can group all of Euler's papers. And then he's going to show you how you can take the papers and using those index numbers before, these Roman numerals, so when they were originally listed by date of publication, he's going to show how each of those papers fits into this classification scheme. So for instance, Diophantine analysis was the third section. And the first part of Diophantine analysis was determination of two or more unknowns given by one equation and impossible equations. Now, one of the things I love about this organization is he could have just pulled out all of these problems and then just listed within this section by the date of presentation. But there's actually some nice ordering where you kind of start at the beginning, kind of the natural introduction to the topic, and build up from there. So for instance, one of Euler's initial papers in number theory, the second one he presented, was the problem of solving equations that looked like this quadratic. ax squared plus bx plus c is equal to y squared. Looking for whole number and rational solutions to that. Now, in order to fully understand that equation, you need to understand how to get solutions to a related equation called Pohle's equation. So pedagogically before this comes a paper, or two papers, that Euler published at an earlier date. Equations, the Pohle's equation, ax squared plus 1 equals y squared. Once you're able to solve equations like this more complicated equation can be transformed into something like this. So pedagogically speaking, it makes sense to present these two papers first, and then you can more fully understand the solutions presented here. And this is done for every section in that classification scheme. So this is part of the systematic index of the Commentationes Arithmeticae. Now, one of the miscellaneous things, one of the unedited manuscripts that we see appearing in the Commentationes Arithmeticae is this manuscript that Euler started to write. And I'm very excited at the prospect of this. Some of Euler's most famous books include the Introductio and the Calculus Differentialis, and his textbooks that he wrote were just wonderful, pinnacles of understanding for the time. And the fact that he was in the process of doing something similar for number theory, I'm incredibly excited about this. Sadly, it wasn't finished, but this is what we do have. There's actually 16 chapters were written in this book. It kind of abruptly stops at the end. But he's got an agenda. He's going for something. And he starts off at the very beginning and he talks about the composition of numbers. And it's almost Euclidean. He says, a number is made up of, 1 plus 1 plus 1 plus 1, and this is what I mean by a multiple, and a times n, that could mean I add n to itself a times, or I could add a to itself n times. And, assuming you know almost nothing about arithmetic. And then he slowly introduces the idea of primes, and he's building things up very, very slowly, but very firmly. So he starts talking about divisors and the sums of divisors and relatively prime numbers. And so things progress to more and more difficult problems. So we start talking about remainders or residues, and what if you have an arithmetic sequence? What if you divide every term in that sequence by a prime? What remainders do you get? Oh, what if you have a geometric sequence? What if you divide every term in that sequence by a prime? What's the pattern of numbers you're going to get? Which numbers will always leave you a remainder of 1? Which powers will leave you a remainder of 1 when divided by a prime? And then, let's see, we're taking a look at divisors of numbers of the form a to the n plus or minus b to the n. And then there's kind of a nice group of 4 which all go together. If you divide a square number by a prime, if you divide a cube by a prime, a quartic by a prime, or a quintic by a prime, what kinds of remainders do you get? And so in particular, dividing a square by a prime might remind you of quadratic reciprocity a little bit. Then kind of a variation on chapter 10, dividing squares by primes. What if you divide a square by a composite number? And then he starts to talk about forms a little bit. He starts to talk about numbers which are the sum of 2 squares, numbers which can be written the form x squared plus y squared. What can you say about the divisors of that? Does every divisor of the sum of 2 squares, is it also the sum of 2 squares? Maybe the prime number divisors of the sum of 2 squares is also the sum of 2 squares. All sorts of fun questions you can ask about the forms of divisors of that. And then, okay, well, the next logical step, once I do the sum of 2 squares, a more general quadratic form, x squared plus 2y squared. What can you say about that? And then he stops. And so one of my big questions is, if Euler, had another 10 years to look at this and continue working on this, what would come next? My gut tells me it would be x squared plus 3y squared, then 4y squared, maybe? More likely x squared plus 5y squared. Then at what point would he stop with forms, and then what would he do next? So one of the things I've been working on recently is kind of going back and forth between these two lists, the chapters of the number theory textbook and then the sections in the Commentationes Arithmeticae. I'm working under the assumption that Euler wanted to kind of categorize all these different problems he worked on and put them in some order from which people could learn. And a lot of the things which appear in 791 also appear in 792. For instance, prime factors and primes and sums of divisors of numbers. We can find most of those. Here's divisors of numbers. Here's sums of divisors of numbers. So Euler's drawn on that material. What else does Euler have in here? He's got divisibility of different formulas or forms. That kind of appears at the end right here. Divisors of numbers which can be written in this form. Divisors of numbers which can be written in this form. Euler still has a lot to say on that. What else is there? Theory of remainders and quadratic residues. That's also right here. So we've got residues, remainders and residues. Think of those as interchangeable for this talk. If you divide a square by a prime, what kind of residues would you get? In the second section, decomposing numbers into different forms and sums of forms. See some of that as well. But one thing which struck me when comparing these two is that Diophantine analysis. This is over half of Euler's number theory right here, is trying to solve these kinds of equations. So I've been reading through here. Let's see. Nothing about solving equations, nothing about solving equations, nothing about solving equations. Now, is it possible that Euler would talk about that at some point? I certainly hope so. Why are we building up this particular tool set? Does Euler have some kind of a goal in mind? A previous talk that I gave involved one of Euler's papers, E272. It was actually about divisors of numbers of the form x squared plus 3y squared. The reason Euler got interested in divisors of numbers of the form x squared plus 3y squared is actually related to Fermat's last theorem. If you write a number as a sum of cubes, you can do a little bit of mathematics and then, introduce extra variables. And something about x and y, they have to be in a form which is related to the quadratic form, x squared plus 3y squared. And so if you know about properties of numbers of this form, then that's actually a huge tool you can use in Diophantine analysis. So I'm thinking that maybe after Euler kind of builds up all the different tools he used in the process of solving Diophantine equations, maybe then he'll actually start showing us how to solve the Diophantine equations. Euler was always very pedagogical, and he wants to show you how to solve equations in their generality. He starts out with examples and moves on to more general things. I'm very excited about this, and also I've been working on translating this and incorporating a lot of this into the Euler Archive. So there's a wealth of information. It's amazing that we still haven't kind of mined this for all of its worth yet. I mean, there's a lot of things which I'm learning about Euler's number theory. For instance, the fact that he spent time, working with quintic equations and dividing them by primes and seeing what kind of remainders you get. I'm interested in how this relates to his other papers, but also, what's the big picture? Why was Euler interested in each of these? Was it, a tool just for solving Diophantine equations? Maybe some of these, he was just interested in it for fun. Are these problems like the Knight's Tour problem? He just did it for fun. It's for recreational purposes. Or is there something more? So these are kind of the three things that I'm trying to work on at the moment now. First is figuring out what comes next. What are the next chapters of E792? And then trying to line up these two pieces of information, not only with each other, but with the contents of the Euler Archive as well. Because the Euler Archive, again, very closely resembles the introduction to the Commentationes Arithmeticae. You could actually view everything kind of in their Enistrom indexed order. But then what do you want to use the Euler Archive for? Well, you might be interested in Euler's work on partitions. You might be interested in his work on Pell's equation. There needs to be some way to kind of pull out those pieces of information. So I've been working on incorporating some more kind of data analysis tools into the Euler Archive. Scan each one of these for a mention of Pell's equation and add them to a list. Or filtering something kind of, using an Euler diagram or a Venn diagram, everything which involves partitions and everything which involves generating functions. Find all the papers which have both of those. So this is very much a work in progress. This is where I am, just kind of having fun looking in E791 and E792, aligning them with each other and the Euler Archive. And it's kind of short, but that's it. Thanks for listening.
There's certainly time for questions.
Yeah. Walter.
I'm just wondering, idly, you might have a better idea about this. Why did he stop making that table of contents?
Oh, why did he stop here?
Yeah, I mean,
I imagine he passed on at that point.
Chapter. We're talking about a table of contents.
Oh no, there's actually, these 16 chapters have been written.
Oh.
Right, this is actually a 75-page manuscript.
Okay. So that certainly will change the answer, but still it's an interesting question. Why did he stop? I mean, he had a lot of things that he was interested in, but is there something more?
I mean, the question is, since it was a manuscript and was never published, we don't know when Euler stopped or even if he did stop. Maybe he was working on this up to the day of his death, I'm not sure. Yes?
I take it he didn't write the manuscript for a preface or introduction, outline what the whole thing is.
No, he was actually, if you want, I can actually show you part of what this looks like. If I hop on over to the Euler Archive. Let's see. So as I was mentioning before, our number theory is just kind of listed solely by topic at this point. But I'm looking for 792. So right, each one of these chapters, again, it's got a very Euclidean feel. He's talking about, a number is a multitude of unities, and here are some numbers. And he starts talking about successors, and a plus 2 succeeds a plus 1 I 1. Right, this is very fully written. He actually numbers the results, and I think he gets up to a total of 850 something paragraphs. Maybe 500 something. And not 850, 580. So he's trying to give a common break.
When Euler speaks of primes, he is really speaking of what we call non-decomposable numbers. The notion of the difference between primitivity and
Yes.
very post-Eulerian.
Right, so...
So what did the word prime mean to him?
So this is a funny thing. It kind of relates to an argument I always have with my students. A prime number has no factors, but every prime number does have factors. It has one and itself as a factor. So Euler actually struggles with this a little bit when he starts talking about sums of divisors, and he observes that for all prime numbers, if p is a prime number, then the sum of its divisors is p plus 1. He kind of uses that to characterize primes a little bit, and that's the basis of his argument for excluding 1 from the set of primes, because the sum of divisors of 1 is 1. So initially it's kind of a very gut feeling, you can't break it into parts, but I'd say that's how he kind of comes to terms with a prime number has 1 and itself as factors, and those factors are different. I'm not sure how much that answered your question.
You pointed out that you proved that as a theorem.
Yes.
Divides A, divides A.
Yes.
That's what they said.
Oh, Euclid's on. So you could use that to actually characterize the prime numbers. Yeah. Let's see, on the divisors of numbers, let's see if we can figure this out. Yeah, my Latin isn't that good, but I'm sure he actually tries to define prime number in here at some point.
What did Gauss know that Euler did? What had happened between Euler and the next giant, Gauss?
When I think of Gauss, I think of the proof of quadratic reciprocity. And it's a fun right, so Euler had kind of done some special cases of quadratic residues, and he had actually thought about it a little bit.
Information that Gauss had that Euler didn't have. Gauss, we know, made use of people who were savants, who could do a huge amount of arithmetic.
I mean, I think Gauss finished proving a lot of things that Euler had not yet formulated or figured out how to say exactly. So I think Gauss kind of ran with the quadratic reciprocity part of what Euler had been working on. I'm not sure what he knew that Euler didn't, he just kind of continued to develop the same topics and formalize and structure them a little bit more.
I have a few questions if it's okay. First of all, this is actually part of 792.
Right, so the first time that 792 was published, this manuscript was published as part of 791. But it also got its own Enström number as well.
Is that true of all of the unpublished, previously unpublished things that were in 791?
I think so. I think there were a total of 4 or 5 manuscripts, and they all have Euler numbers, I think in the late 700s or 800s. So odds are this was the first time a lot of things appeared.
So Chebyshev was responsible for this collection.
Yes, he had a little bit of help from Jacobi as well for getting records from the Berlin Academy, looking for his manuscripts there as well. But Chebyshev was kind of spearheaded this part.
Did he write in French? I mean, I know the articles are in whatever language Euler wrote them in, but...
The Commentationes Arithmeticae is itself in French. So if we actually, let's hop back to 791, which ironically isn't part of this, but if I head over to 791, like Google Books has conveniently saved us the difficulty of scanning this entire thing. Let me show you a little bit of the, let's see, so you've got kind of the standard stuff in an Euler volume. You've got a list of the papers he wrote. You're going to have the eulogy. Then the very interesting part.
You read much faster than I do.
No, I just know how to skip to the great stuff. So yes, so this is Chebyshev, and kind of the project was spearheaded by Bunyakovsky, but he brought Chebyshev in here. And this is actually completely in French.
Now, did they speculate at all about when Euler
I don't think so. I mean, I think the only note they gave was it was something which was not published. Head back down to that. Right, we're almost there. Right, so here's actually the piece of the record I had shown you before, and whenever they know anything about the publication date, it's always in there. to 1772. Oh, this is just Commentations Volume 1. The rest would be in Volume 2. Oh, too far. Right, so
these are the unpublished.
right, I don't think they make any guess as to when it was written. My basis for assuming this is back in the first volume, in one of the slides I showed you. The second paper of Euler's wasn't presented, but they estimated a date of writing to put it at the right time in the list. So in this case, the fact that it wasn't exhibited at all, they didn't even try to guess. So it would be inserted there, Rochelle. Is there?
Yeah. After 492 is 592 instead of 492.
You're right. Darn that,
Yeah, but that's not your typo, is it?
No. This is actually Google has done a lot of scanning of original sources as well. And this is actually the 1849 edition, I think. So this was an original typo.
Yes.
So I'm not sure if they tried to estimate when he wrote that, Rob. Yes, sir.
Somewhere in the world, some group of Euler fans, possibly in this very room, are trying to finish his book.
Anybody trying to finish it in this room? Looks like no.
Is it possible?
Oh, is it impossible to finish it? No. I mean, it's going to be conjecture to a large extent. You know, you could do the quadratic forms, but after that, you know, would he have included Diophantine equations? I'm not sure. That seems to be a nice idea. It's hard to get in Euler's head. I like to think that, yes, he would have shown us how to use these tools to solve equations. That's my best guess, and it's just a guess.
Is there any chance that there's any significant amount of missing Euler stuff?
It's possible. I'm surprised it wouldn't have turned up by now. I'm sure people have gone through the archives at Berlin and St. Petersburg with a fine-tooth comb by now. But it's always possible, I guess.
Manuscript. Is there a way to see the actual manuscript? And this is written.
Oh, the original manuscript.
Which they must have been, Chebyshev must have been working from the manuscript.
Right. Yeah, so there must be an extant manuscript somewhere. But where it is, I'm not sure.
Almost certainly Petersburg, if Chebyshev had access to it.
But would they have turned over that manuscript to, say, the Euler Commission in Basel? Not sure where it would be now. But I bet there's a likely list of suspected locations, 3 or 4 long, where the manuscript currently sits.
There might be information on where the manuscript is in the Euler Archive. In fact, they probably would have some information. A lot of these unpublished papers were in, what was the later, pardon me,
The Opera Postuma?
Opera Postuma, right, and so they would have been transcribed from literally handwritten documents at that point. So this was probably, just a guess, transcribed at the time that Chebyshev was putting this volume together. But yeah, somewhere there's a original document. Probably says so in the Opera document.
Sounds good to me.
Well, it was a big letter writer.
He did, yeah.
Did he mention this textbook of his, this number theory textbook, in any of his correspondence?
Well, not with Goldbach, because I'm pretty sure that... Actually, no, I'm not sure. Maybe. I'll get back to you on that. I'm inclined to say no, but now I'm going to say maybe.
It's not a quiz.
Nope.
It's quite possible that he started this later in life. Goldbach was people that thought that number theory was interesting. but one of the reasons why it may not have appeared was this wasn't considered the important piece from mathematics. Other questions or comments? Well, then let's thank Lee once again for